Welcome to Tolofson Physics. So what we're going to do is now we're going to look at a couple situations and we're going to apply a force diagram, but now we're going to add some numbers to it. So these are going to be quantitative force diagrams. So what we're going to do in this first case is we're going to look at a, not that one, we're going to look at a wagon that we're pulling, but we're going to pull it parallel to the surface of the ground. And so that actually makes for quite a simple force diagram when we do it that way. So I will go ahead and draw a force diagram for that first. So what we're going to do is we're going to look at what forces are acting upon the wagon itself. So I'm going to draw it around the wagon up to the person's hand, and we'll do it from that. So I'm going to draw my center of mass, and then we always have, on Earth at least, the force due to gravity. So I'm going to go ahead and start with that right away. And now let's look at what else must be going on. Well, first off, this is touching the ground and it's touching the person's hand. So we're going to keep that in mind. And so touching the ground, the molecules are holding up the molecules of the wagon. And so we have a normal force that is holding that up. And in this particular case, the up force is going to equal the down force, and there's no other up and down forces, so I can indicate it that way. Now, let's see. I'm saying that this is being pulled with a 5 Newton force, and I'm just going to call it a pull, because really, a force is a push or a pull. Could I call it an applied force or a tension force in this case? Sure, why not? But the idea is I'm pulling it with 5 Newtons of force. And then what I didn't say before is this is going to move at a constant velocity. So this is going to be a balanced force diagram. So the net force is going to equal 0. So there must be some sort of backwards force that is causing that to move at a constant velocity. And so most likely that's a frictional force. Since I drew a wagon, it's probably the friction within the axles of the wheels rubbing there, causing it to slow down, or causing it not to just keep moving, or in this case. So we have a balanced force. And so my right force equals my left force. And basically I can just look at this force diagram. I don't even have to write any equations to figure this out, because if my right force is 5 newtons, well, my left force is 5 newtons. What about my up and down force? Well, I can calculate the force due to gravity using the mass times the acceleration of gravity, in this case on Earth. And so what we're going to use is, when we're doing problems, we're going to round it to 10. But if we're doing lab work, we're really going to have to use 9.8 newtons per kilogram, because that's what it is. It's a little bit closer to that in reality. But for problem solving, we're going to round it to 10 because we can do that math on our head. And so up here, I wrote that this is a 20 kilogram mass, and I'm going to multiply it by 10 newtons per kilogram. Now, newtons per kilogram are identical to meters divided by seconds squared. All right, so this is kind of a handy trick, because when I express it this way, then I realize, yeah, this number needs to be in kilograms, and once it's in kilograms, I can cancel those units out, and I end up getting, I'll have to write it above it, 200 newtons of a gravitational force. And so since I know that this is 200 newtons in the downward direction, well, then I know that it must be 200 newtons in the upward direction as well. And so there you go. There's a fairly simple force diagram for something moving on the horizontal where all of the forces are perpendicular to each other.